When we think of Mars, we think of rust and emptiness. A frozen desert world, a graveyard of failed dreams, a monument to planetary decline. For most of the 20th century, that image stuck. Mars was presented as a cautionary tale, a planet that once had water, once had potential, and then lost it all. The idea was simple and satisfying. Mars was geologically dead. It had cooled, contracted, and shut down billions of years ago. Its magnetic field collapsed. Its atmosphere escaped to space. Its water froze or disappeared. The story was one of abandonment, not mystery or ongoing change. We were comfortable with that narrative. Mars became a reference point in planetary science, a marker for what happens when a planet is too small to maintain its internal heat engine. Lose your magnetosphere, and your atmosphere gets stripped away by the solar wind. Lose your atmosphere, and your water evaporates or freezes underground. Lose your internal activity, and you're done. The planet becomes static. Mars fit that pattern perfectly. It was what we expected a dead planet to look like. Scientists didn't expect Mars to surprise them anymore. The basic story seemed written. The Mariner missions in the 1960s showed us a cratered surface. The Viking landers in the 1970s confirmed a harsh, frozen surface with a thin carbon dioxide atmosphere. Pathfinder in the 1990s added more detail, but didn't challenge the fundamental assumption. Mars was geologically inactive and had been for billions of years. Even the discovery of ancient riverbeds and evidence of past water only reinforced the narrative of decline. Water had flowed once, then it stopped. Mars had changed, but not recently. That comfortable story started to crack in the early 2000s, first with the Mars, then with Mars Express, and then explosively with the Mars Reconnaissance Orbiter. The data that came back didn't match the old model, fresh gullies appearing on slopes where nothing had been visible before. Seasonal variations in atmospheric gases that shouldn't exist on a geologically dead world. Methane plumes from the subsurface. Dark streaks on crater walls that grew and faded with the seasons. Evidence of relatively recent impacts still showing heat signatures. And most surprisingly, signs of ongoing geological activity happening not billions of years ago, but within the last few million years, within the last few thousand years, possibly within the last few years. Mars wasn't supposed to do that. Mars wasn't supposed to be changing. But it was. The deeper scientist, the more active the picture became. The turning point came when these observations couldn't be ignored anymore. When multiple instruments from multiple missions all showed the same thing. Mars is still doing things. Mars is still moving. Mars is still evolving. This matters because it changes everything about how we understand planetary evolution, habitability, and the prospects finding life past or present. If Mars is still geologically active, if its subsurface still holds heat and water, if it's still changing, then the possibilities expand dramatically. A dead planet is one thing. A sleeping planet is another, and that's what Mars turned out to be. Not dead, sleeping, and slowly waking up to our instruments just as we've developed the technology to finally listen. To understand Mars's activity was so unexpected, you have to understand what we thought we knew about planetary death. The story starts with size and physics. Mars is a small planet. Its diameter is 6,079 kilometers, making it about half the size of Earth and only slightly larger than Mercury. In planetary terms, it's barely more than a large rock. And that size matters enormously. When a planet is born from the solar nebula, it inherits heat, radioactive elements in its interior. Uranium, thorium, potassium decay continuously, releasing energy. This internal heat drives everything: volcanism, plate tectonics, magnetic field generation, and mantle convection. A large planet like Earth has so much mass that this heat stays trapped inside, leaking out slowly through the crust over billions of years. A small planet is different. Heat escapes more easily because there's less insulating material above the core. The surface-to-volume ratio works against it. Mars, being small, should have cooled much faster than Earth. The theory predicted that Mars should have shut down early. Its magnetic field, powered by a convecting liquid outer core, should have stopped generating around 4 billion years ago. Without a magnetic shield, the solar wind, that constant stream of charged particles from the Sun, should have stripped away Mars's atmosphere. Without an atmosphere, liquid water couldn't exist on the surface. Without geological activity to replenish it, Mars should become a frozen, inert desert relatively early in solar system history. The model was elegant, mathematically sound, and seemed to match what we observed. For decades, that was the consensus. Mars cooled, Mars died, case closed. But there were always little oddities that didn't fit perfectly. The magnetic anomalies detected Mars Global Surveyor in 1997. Instead of a global magnetic field, Mars had localized magnetic zones scattered across its surface, particularly in the southern highlands. This was strange because it suggested Mars once had a global field that shut down, but the anomalies remained fossilized remnants of an older magnetosphere locked in the crustal rocks. That part made sense with the model. But there was something else. Some of those anomalies were stronger and sharper than they should have been if they were just ancient rocks. They looked, in some ways, like they'd been created more recently than the theory suggested. Then there was the atmospheric methane. In 2003, scientists' ground-based telescopes detected methane in Mars' atmosphere. Methane down under ultraviolet light within about 300 years. So if methane is present now, it has to be replenished. It has to be coming from somewhere active, somewhere that's generating it recently. On Earth, methane comes mainly from biological sources. But it can all come from geological processes, from the interaction of water with certain types of rock deep underground, a process called serpentinization. If Mars has subsurface water and the right rock types, it could generate without any biological process at all, but the methane had to be coming from somewhere active. That meant Mars wasn't completely dead. The Gully discovery came next and really challenged the old model. Mars Reconnaissance Orbiter started taking high-resolution images of Mars's surface, and researchers noticed something remarkable. There were narrow channels carved into cliff sides and crater walls, gullies that looked like they'd been carved by flowing water. And they were fresh. In some cases, these gullies appeared to be changing, growing, or becoming more pronounced between imaging passes separated by just a few years. If water was flowing on Mars now, or even recently, then Mars was still active. Its subsurface had to contain water, and that water had to be reaching the surface through some mechanism. The leading hypothesis involved seasonal variations. During certain times of the Martian year, when temperatures rose slightly, subsurface ice might melt or hydraulic pressure might force water to the surface. Water would flow for a brief period, deepening these gullies, and then it would freeze again. But this process required a subsurface that was still active, still capable of moving water around, still capable of responding to seasonal changes. That didn't fit the dead planet model either. Then came the dark streaks. Researchers analyzing Mars Reconnaissance Orbiter images noticed dark marks appearing on slopes during warm seasons and fading during cold seasons. The most prominent ones were on a crater wall called Newton crater. Year after year, streaks would appear in the same general locations. Some streaks fade completely, then reappear the next season. This pattern repeated multiple times, captured in image after image. The leading explanation was that these were caused by briny water trickling down the slope, loosening dark dust and revealing lighter material underneath, or possibly the water itself caused mineral changes that created the dark appearance. Either way, something was moving on Mars's surface seasonally. Something active, something that responded to changing conditions. This discovery was revolutionary because it suggested Mars wasn't a static, unchanging world. It was a world that responded to its environment. It was a world that moved. But here's where the old model started to completely break down. If Mars had no global magnetic field, if its atmosphere was thin and fragile, if it was a small planet that should have cooled early, how was it still moving water around? How was it still doing anything? The answer had to involve a subsurface that was more active than the models predicted. If there was still heat underground, if there was still water locked in bound in minerals, if there were processes churning away below the surface, then Mars isn't dead. It was dormant. And dormant worlds can wake up. The real turning point came with the seismometer. When NASA's InSight lander touched down on Mars in November 2018, it carried an instrument designed to listen to the planet's interior. This seismometer, called SEIS, was exquisitely sensitive. It could detect vibrations far too small for any human to feel. Vibrations caused by the planet's internal activity. Nobody really expected SEIS to detect much. Mars was supposed to be seismically quiet. If it was geologically, it shouldn't be shaking. But SEIS immediately started picking up tremors. Marsquakes. Weak by Earth standards, most of them registering as magnitude 3 or 4 at most. They were there. And they kept coming. Over the course of InSight's mission, SEIS recorded hundreds of marsquakes. The implications were staggering. These weren't random vibrations or equipment artifacts. They were genuine seismic events caused by stress and movement in Mars's crust and upper mantle. They clustered in specific regions associated with known geological features, like the Cerberus Fossae system of Fast and fissures in Mars' equatorial region. The frequency and distribution of these quakes did that Mars's interior was still under stress, still deforming, still moving. One particularly significant finding came from the analysis of marsquake waves. When an earthquake happens on Earth, seismic waves travel through the planet's interior at different speeds, depending on what type of material they pass through. A thin crust gives way to a thick mantle, gives way to a liquid outer core, gives way to a solid inner core. By analyzing the marsquakes details, scientists could infer the structure of Mars's interior. And what they found was that Mars's core was still at least partially liquid. A liquid outer core means heat is still moving around into the planet. It means internal convection is still happening. It means Mars isn't completely dead. The heat flow measurements from InSight added more data. The lander included a heat probe to measure how much thermal energy was escaping from Mars's interior through the surface. The measurements showed that Mars was releasing about 4.9 watts on average, with significant regional variations. Compare that to Earth's heat flow of about 0.1 watts per square meter, and Mars seems relatively cool. But compare it to what models of a completely dead planet would predict, and it's surprisingly high. Mars is still bleeding heat into space. That heat has to come from somewhere, and most of it comes from radioactive decay in the interior. The fact that Mars is losing heat at this rate suggests that something down there is still active, still moving, still processing that interior heat and bringing it to the surface. These findings challenge the widespread assumption that Mars had cooled to near total inactivity. The seismic data suggested ongoing stress and deformation. The heat flow measurements suggested interior dynamics. The two pieces of evidence together painted a picture that hadn't completely shut down. It had slowed down tremendously compared to its earlier history. But it hadn't stopped. The marsquakes also revealed something about Mars's recent geological history. Some of the strongest quakes detected by sea ice seem to be associated with relatively young geological features. The Cerberus fossae, where many quakes were concentrated, showed signs of recent tectonic activity. Lava flows in that region appeared to be among the youngest on Mars, possibly as recent as a few million years old. This suggested that Mars had experienced a pulse of activity relatively recently in its history, recent in geological terms, which on a planet billions of years old still means millions of years ago, but recent compared to the deep past. More intriguingly, some of the marsquakes seemed to cluster in patterns that suggested they were connected to thermal convection in the subsurface. As material rose from deeper layers and cooler materials sank, it created stress on the overlying crust. That stress built up over time and then released as earthquakes. This is normal on a geologically active world like Earth. But Mars was supposed to be too cold for this kind of sustained convection. Yet here it was happening. InSight's mission ended in December 2022, when dust storms cut off the lander's power supply. The solar panels couldn't generate enough electricity and the lander went silent. But the data it had collected over 4 years provided an unprecedented window into Mars' interior, and that window revealed a planet that was still alive, still shaking, still moving. Among all the discoveries that have challenged the dead Mars narrative, perhaps none has captured more attention and controversy than the methane question. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms. On Earth, it's associated primarily with life. Bacteria produce methane as a byproduct of metabolism. Termites produce it. Cows produce it. Most atmospheric methane comes from biological sources, but methane can also form through purely chemical processes. When water comes into contact with certain iron-rich rocks, particularly in the absence of oxygen, chemical reactions can produce methane. This process, called serpentinization, happens on Earth's ocean floors, and potentially happens on Mars too. The first detection of methane in Mars's atmosphere, announced in 2003, was tentative. Ground-based telescopes on Earth can detect methane if concentrations are high enough and viewing conditions are favorable. But the measurements were at the edge of detectability. Some observers questioned whether the signal was real or just noise. But over the following years, multiple observations confirmed it. Methane was definitely present in Mars's atmosphere. Then came a puzzle. The concentration of methane seemed to vary seasonally. It was higher in some seasons and lower in others, and it seemed to vary geographically. Some regions showed more methane than others. This variation suggested a source that was active now, not something left over from Mars's ancient past. And the concentrations seemed to change faster than they should if methane was just being produced at a constant rate, and then destroyed by ultraviolet light. The Mars Express orbiter carried an instrument SPECIM that confirmed these variations. The methane concentrations were real, they were changing, and they seemed to come from localized sources. The strongest concentrations were detected over regions like Gale Crater, where the Curiosity rover was operating, and Hellas Planitia, an enormous impact basin in Mars's southern hemisphere. If you plotted the methane detections on a map, they clustered in certain areas. That clustering suggested specific sources, not global distribution. This raised an extraordinary possibility. If methane was being produced now, if it was coming from active sources beneath the surface, and if it was reaching the atmosphere through vents or diffusion, then Mars might have subsurface environments where chemistry or biology could operate. The subsurface of Mars, where temperatures are warmer and where liquid water might exist in small quantities, could potentially harbor microbial life. Not on the surface, where radiation and cold would kill anything we know of. But below, in the protected depths, life might persist. The rover missions started searching for clues. Curiosity, which landed in Gale Crater in 2012, included a sophisticated analytical instrument called SAM sample analysis at Mars that could detect organic compounds. The rover drilled into rocks, vaporized the samples, and analyzed what came out, and it found organics. Carbon-containing compounds that could be remnants of ancient life, or could have formed through non-biological chemistry. Notably, the organic content seemed variable, sometimes higher, sometimes lower, possibly seasonal in nature. More intriguingly, Curiosity detected methane spikes in Gale Crater. When the rover would drill into certain rocks and heat them up for analysis, the samples would sometimes release bursts of methane. This could mean that methane was trapped in the rocks themselves, locked away in mineral structures, waiting to be released. Or it could mean that, as the sample was heated, chemical reactions created methane. Or it could mean that contamination from Earth was responsible. Each possibility had to be carefully considered. By 2023 and 2024, the picture had become more complex. Different missions and instruments were measuring methane with varying results. Sometimes the concentrations were higher than previously detected. Sometimes they seemed lower. Ground-based observations sometimes conflicted with orbital measurements. The rover detected methane pulses that seemed to come from the local area. But the global atmospheric methane was harder to pin down. This is where the story gets interesting, because it reveals something important about how science works. The methane question isn't settled. It's not clear whether Mars is producing methane actively right now, or whether the detections represent leftover methane from earlier epochs that's being released slowly as surface conditions change. It's not clear whether the methane comes from geological process or from something biological. It's not clear whether different detection methods are measuring the same thing, or whether there are systematic errors in some of the measurements. What is clear is that Mars isn't uniform. It's not a bland, homogeneous wasteland. It has regions with detectable methane. It has subsurface reservoirs of volatiles. It has places where underground water might reach the surface seasonally. It has environments not on the surface, but beneath it, where liquid water could exist. And given that life arose on Earth in similar subsurface environments 4 billion years ago, the possibility that similar might have happened on Mars can't be dismissed. The methane mystery matters because it keeps reminding scientists that Mars is still not fully understood. There are processes happening, there are sources of volatiles, there are active regions. Mars isn't a dead rock with fossils of past activity. It's a place where things are still occurring, where underground chemistry is still happening, where the basic building blocks for habitability, water, chemical energy, and some degree of heat might still exist. Mars's atmosphere is thin. On the surface, the atmospheric pressure is about 600 pascals less than 1% of Earth's atmospheric pressure at sea level. It's composed primarily of carbon dioxide, with small amounts of nitrogen, argon, oxygen, and trace gases like methane. If you stood on Mars without a suit, you wouldn't just freeze and suffocate. The air pressure would be so low that any liquid in your body would boil away. It's a hostile environment. Yet despite this thin, apparently stable atmosphere, scientists have discovered that Mars's atmosphere is far more dynamic than anyone expected. It's changing seasonally. It's exchanging mass with the surface and subsurface. It's being lost to space, but not at the catastrophic rates that early models predicted. And in some cases, the atmospheric processes seem to be creating conditions for transient liquid water that exists only briefly, only in certain places, only under specific seasonal conditions. The seasonal dynamics are particularly interesting. Mars's orbit is more elliptical than Earth's and Mars's axis, giving it seasons. When Mars is at perihelion, its closest to the Sun, it receives more solar energy. This happens around Mars's southern hemisphere summer. The heating causes carbon dioxide to evaporate from the polar ice caps. The atmospheric pressure rises. Winds increase. The entire atmospheric circulation pattern changes. As the atmosphere thickens slightly during these warm periods, temperatures in certain regions increase enough to potentially allow liquid water to exist briefly. The famous recurring slope line, the dark streaks observed by Mars' reconnaissance orbiter, appear to be connected to these seasonal cycles. During warm seasons, subsurface water somehow reaches the surface, flows downslope for a brief period, and then neither evaporates or refreezes. The streaks are the evidence of this flow. They don't persist year-round because the water doesn't persist. They return season after season, suggesting a cyclic process tied to atmospheric and thermal conditions. One particular region has proven especially interesting: the Valles Marineris system. This vast network of canyons runs along the equator, stretching over 4,000 kilometers. Within these canyons, there are areas where gullies seem to be particularly active. Some researchers have proposed that these gullies might be cut by CO2 and avalanches of frost and dry ice during certain seasons, a process that doesn't require liquid water. But other evidence suggests real water flow. The question remains open, but the key point is that something is moving, something is flowing, something is carving these features. The atmospheric law story is also more nuanced than the simple narrative suggested. Yes, Mars is losing atmosphere to space. Solar ultraviolet radiation breaks molecules apart and creates ions. The solar wind sweeps these ions away. Over billions of years, it has stripped away most of Mars's atmosphere. But the rate of loss today isn't as high as it was earlier in Mars's history. Various factors affect the loss rate. The strength of the solar varies with the solar cycle. The tilt of Mars's magnetic anomalies changes the local shielding from solar wind, and seasonal atmospheric variations mean more molecules are available for loss at certain times of year. The Methane spacecraft, Mars Atmosphere and Volatile Evolution, which has been orbiting Mars since 2014, was specifically designed to measure atmospheric loss. Methane has shown that Mars is losing atmosphere at a rate of about 100 grams per second into space. It's a significant amount over billions of years, but not as catastrophic as some models suggested. More importantly, Methane has shown that the loss rate varies dramatically. During powerful solar storms, the loss rate spikes. When solar activity is low, the loss rate drops. This means Mars's atmosphere is more resilient than a simple model would suggest. It survives better during calm periods and can be stripped more quickly during active periods. But perhaps most remarkably, MAVEN has detected evidence of atmospheric recycling. Some of the atoms being stripped from Mars's atmosphere don't escape to space. Instead, they're initially accelerated away, but then Mars's weak gravity and weak magnetic field can sometimes turn them back around. They fall back to the surface or stick in temporary orbits. This means Mars's atmosphere is trapped in a complex dance with space. Some molecules escape, some return, some get temporarily captured by Mars's magnetic anomalies, and then released again. The thin atmosphere also interacts with the surface in complex ways. Wind-driven erosion is slow on Mars because the air is thin and wind speeds need to be extremely high to move significant quantities of dust. Yet erosion is happening. Dust storms rise seasonally, sometimes growing to planetary scale, covering the entire planet in a global dust veil. These storms affect temperature, atmospheric circulation, and solar radiation reaching the surface. They're not permanent, they fade after months, but their seasonal occurrence shows that atmospheric dynamics are still actively shaping Mars's surface. One particularly dramatic example came during the 2018 global dust storm, which coincided with Opportunity rover's final days. The rover, which had been operating since 2000 solar-powered. The dust storm cut off so much sunlight that the rover's batteries drained. Communication with Earth was lost. Opportunity never came back online, but the storm itself was scientifically valuable because it demonstrated that Mars's atmosphere is still capable of dramatic changes, still capable of affecting surface conditions in significant ways. A dead planet with a dead atmosphere wouldn't have global dust storms. For decades after the discovery of ancient river channels and lake beds, the assumption was that all of Mars's water was gone. It had evaporated to space. The small amounts that remained were frozen in the polar ice caps or locked deep underground in permafrost. Mars was dry. That was the consensus. But that consensus has crumbled as imaging technology improved, and we learned how to read Mars's G more carefully. Water ice is formed at Mars's north polar cap. That's obvious and has been known for a long time. But we've also found water ice at the south polar cap, mixed with dry ice. More surprisingly, we've found water ice in craters and depressions at mid-latitudes, places where it shouldn't exist according to simple climatic models. We've found it near the subsurface, exposed by recent impacts that have created young craters with bright interiors. We've found that the waters that are still actively exchanging with the atmosphere, frost depositing on the surface in cold regions, and then evaporating as temperatures rise. The subsurface water story is particularly significant. Below Mars's surface, there are extensive deposits of water ice. Ground-penetrating radar has detected subsurface water layers, particularly in the mid-latitudes. Some of these deposits are extensive regions, hundreds of kilometers, where ice beneath only a few meters of soil. In some cases, the ice deposits are pure enough that if humans ever establish a base on Mars, these regions could serve as water sources. But for the science question, the important point is that water is still there, still present, waiting beneath the surface. What changed our understanding was the realization that this subsurface water isn't completely static. It moves. It exchanges with the atmosphere through a process called cryospheric exchange. Frost forms on the surface in cold regions. That frost contains water molecules from the atmosphere. Eventually, when it's warm enough, Some of that water returns to the atmosphere through sublimation, turning directly into vapor without melting into liquid first. This cycle happens seasonal. It means Mars has an active water cycle, even though there's no oceans, no rain, no weather, as we experience it on Earth. More remarkably, there's evidence that liquid water might exist transiently in the subsurface, even today, deep underground, where geothermal heat from Mars's interior warms the rock. Water could remain liquid even at temperatures far below 0 Celsius. This is possible because when salt is dissolved in water, the freezing point drops. Salty water can remain liquid at temperatures of -10, -20, or even lower Celsius depending on the salt concentration. If Mars has subsurface reservoirs of salty water, and the chemistry of Mars's surface suggests it probably does, then there could be liquid water exist in layers deep underground. Not flowing rivers, not lakes, but liquid water nonetheless, potentially in environments where simple chemistry could operate and where, in principle, life could persist. The recurring slope lineae question ties directly to this subsurface water. Every proposed explanation for how these features form involves water, either as liquid or as frost. If it's liquid water, it comes from subsurface sources that reach the surface through porous layers or fractures. The water flows briefly in the warm season, when underground temperatures above the freezing point of salty water. It carves or deepens the gully. Then it either refreezes or evaporates. If it's frost-driven flow, then carbon dioxide, frost accumulates in the gullies during cold seasons, and when it's warm enough, the dry ice sublimes, creating pressure and jets that mobilize loose material downslope. Either way, the gullies represent seasonal activity driven by energy from the sun and heat from the interior, both sources of energy that are still present on Mars today. The discovery of perchlorates in Mars's soil added another dimension to the water story. Perchlorates are highly oxidizing salts that can lower the freezing point of water dramatically. If Martian soil in perchlorates, then water could exist in liquid form at surprisingly cold temperatures. Some researchers have proposed that this might explain how deliquescence, where salts pull moisture from the air and dissolve into liquid form, could create thin films or small pools of liquid water on Mars's surface, even in the coldest regions, even in the thin atmosphere. The amounts of water would be vanishingly small, but they would be liquid. And that liquid, however thin, represents an active process, something happening now. The ice on crater rims and in shadowed regions near the poles provides another puzzle. These deposits appear relatively young. They haven't been there forever. They're being created or exposed by ongoing processes. In some cases, the ice seems to be growing. In other cases, the changes are slow, happening over decades, but they're real, measurable changes. This indicates that Mars's hydrological cycle, albeit sluggish and operating at a slow pace compared to Earth's, is still active. Water is still moving between different reservoirs between the atmosphere, the surface, and the subsurface. One particularly fascinating discovery involved the detection of water vapor in Mars's upper atmosphere. When Mars Express measured the composition of the upper atmosphere, it found more water vapor than expected, particularly in certain regions and seasons. This water had to come from the surface or subsurface, had to be evaporated into the atmosphere, and was escaping into space. It's another piece of evidence that water mobility and exchange is still happening on Mars, still cycling through different states of matter, still interacting with the atmosphere. The broader implication of all this is that isn't the dry, static world we assumed it was. It's a world where water exists in multiple forms, in multiple locations, in different states. Some water is frozen, some is locked in minerals, some evaporates seasonally, some dissolves in subsurface brines. The picture is of a world with active hydrological processes, albeit slow and subtle compared to Earth, but active nonetheless. When thermal infrared cameras look at Mars, they're not seeing the visible surface in familiar colors. They're seeing heat, the infrared radiation emitted by rocks and soil at different temperatures. These thermal images reveal patterns that visible light photography can't show. They reveal where heat is concentrated, where subsurface materials are being exposed, where young geological features are still in the process of forming. The thermal infrared instruments on orbiters like Mars Express and Mars Reconnaissance Orbiter have shown something remarkable. Young craters on Mars are often warmer than older craters in their immediate surroundings. This makes sense because when an impact occurs, it exposes fresh subsurface material that hasn't been weathered by billions of years of radiation and dust. This fresh material has different thermal properties than the surface dust. It heats up differently under sunlight and cools differently at night. The thermal signal signature persists for a long time after the impact, gradually fading as dust accumulates on the fresh material and weathering processes set in. By analyzing thousands of impact craters with known ages, scientists can create a timeline of recent impacts and recent surface activity. The data shows that Mars has experienced a steady rain of meteorites throughout its history, with some particularly young impacts that occurred within the last few million years, or even more recently. Some craters appear so fresh, their thermal signatures so strong, that they might be a few hundred years old or younger. This level of recent geological activity measured in time frames relevant to human history, in some cases, suggests that Mars is still being shaped by external processes. The impacts add heat temporarily, expose fresh material, and create opportunities for chemical reactions and possibly water mobilization. More intriguingly, thermal imaging has revealed anomalies in regions where no recent impacts can explain the warmth. In certain places, particularly in regions with known volcanic history, the subsurface seems slightly warmer than it should be. This could be explained by better-than-average insulation, by differences in rock composition that affect thermal properties, or by actual differences in geothermal heat flow. If it's the latter, if certain regions really do have higher geothermal heat, implies that Mars's internal heat distribution is uneven, that it's not distributed uniformly through the planet, but is concentrated in certain regions where convection or continued radioactive decay generates more heat. The Tharsis region, Mars's prominent topographic feature, a vast volcanic plateau covering an area roughly the size of North America and rising several kilometers above the mean elevation, shows particularly interesting thermal patterns. Tharsis contains some of Mars's largest volcanoes, including Olympus Mons, the most massive volcano in the solar system. These volcanoes are ancient by Mars's standards, most erupting billions of years ago. But thermal imaging suggests that subsurface heat in the Tharsis region remains notably higher than in surrounding areas. This could mean that the volcanic heat is still present at depth, still affecting subsurface conditions, still potentially able to warm subsurface water and create environments where chemistry or biology could operate. Perhaps most significantly, Thermal imaging has documented some features that appear to show ongoing thermal evolution. Certain regions seem to have changed their thermal signatures between observations taken years apart. This is difficult to study definitively because thermal patterns can change due to dust deposition, surface weathering, and seasonal variations. But some of the changes are persistent and large enough that they can't be explained by these factors alone. They might represent genuine changes in subsurface thermal conditions. This would imply that Mars's heat flow is dynamic, not static, responding to changes in subsurface activity. The infrared imaging has also been crucial for identifying regions where subsurface water might be accessible. By combining thermal data with visible imagery and radar data, scientists can identify areas where ice is buried shallowly, where the subsurface temperature regimes might allow liquid water to exist, and where geothermal heat sources might warm the ground. These maps are being used to guide both scientific investigations and to plan for future human missions that will need water resources. One particularly fascinating application involves using thermal imaging to study the dark streaks that appear on steep slopes. By analyzing the thermal properties of these features, how quickly they heat up and cool down compared to surrounding material, researchers can determine their composition and age. Some streaks appear darker because they're made of finer material that's been mobilized by water. Others appear darker because the texture is different, perhaps because the surface has been altered by chemical reactions with water. The thermal signatures help distinguish between these possibilities. One of the most surprising discoveries in Martian geology has been the evidence for surprisingly recent volcanic activity. For decades, all of Mars's volcanoes were thought to be ancient, with the youngest eruptions occurring hundreds of millions of years ago or earlier. Mars's small size meant its interior should have cooled and shut down early. The volcanoes should all be dead relics from the planet's youth. But when scientists carefully dated the lava flows on Mars using crater counting techniques, analyzing how many impact craters are superimposed on volcanic flows to estimate the flow's age, they found something unexpected. Some flows were much younger than expected. The youngest volcanic flows on Mars, particularly in regions like the Elysium Planitia, appeared to be less than 100 million years old. Some flows looked so fresh, their crater counts were so low, that they might be only a few million years old. This raised an extraordinary question. If the youngest lava flows are only a few million years old, why did the older models predict that volcanism should have stopped billions of years ago? The answer involves the internal dynamics of Mars being more complex than simple models suggested. Mars's interior isn't uniformly cooling. It's cooling unevenly. Certain regions retain more heat. Certain thermal structures, like mantle plumes, where hot material rises from deep in the planet, might persist longer than expected. Under these plumes, volcanism could continue episodically, even as the planet as a whole gradually cools. Evidence for extremely recent volcanism became even more compelling with the discovery of hidden lava flows. In the Cerberus Fossae region, an analysis of the volcanic deposits revealed that one particular lava field, called the Cerberus Rups Formation, dated to approximately 2 to 8 million years ago. But more remarkably, superposed crater analysis suggested that some flows in the region might be as young as 200,000 years ago. If true, this would mean Mars had active volcanism within timeframes that are almost recent in geological terms. The Argia Mons volcano, another massive volcanic construct on Mars, showed signs of eruptions within the last 50 million years. The young lava channels had extraordinarily low crater counts, suggesting minimal surface weathering since the lava solidified. Some researchers proposed that on such a young feature, even the ordinary processes of meteorite impacts and dust deposition would create detectable changes within a human lifetime. In principle, if humans were present on Mars observing these flows over decades, they might be able to detect measurable changes. What drives this volcanism? The heat source appears to be internal to Mars. One major explanation involves the presence of hot mantle plumes beneath certain regions. These plumes bring hot material from deep within Mars's interior upward through the crust. If this material is hot enough, and if there's an easy path for it through existing weaknesses or fractures in the crust, it can melt the overlying rock and create magma. This magma can reach the surface and erupt as lava. The Elysium region, which shows the strongest evidence of recent volcanism, sits above might be an active mantle plume. The numerous calderas, collapse pits, and lava flows in this region suggest repeated volcanic activity. The young ages of these features suggest that activity has continued into surprisingly geological times. Some researchers have proposed that this plume is still active to today, still bringing heat toward Mars's surface, still creating conditions for potential subsurface water mobilization, and possibly ongoing chemical activity. Evidence for recent volcanism also came from studies of volcanic gases. If Mars had active volcanism billions of years ago, outgassing would have released volatiles, water vapor, carbon dioxide, methane, sulfur to the atmosphere. Over time, these gases would have been lost or locked back into the surface. But if volcanism was ongoing, fresh volatiles would be released continuously. Some researchers have proposed that the methane detected in Mars's atmosphere might be connected to recent or ongoing volcanic activity, specifically to volcanism that's actively degassing volatile-rich magma. The chemistry wouldn't make methane directly, but hot rock interacting with water could generate methane through serpentinization, with the heat source being provided by volcanic activity. Additionally, the thermal modeling of Mars's interior that incorporates recent seismic data suggests that Mars could sustain localized volcanic activity even today. The MAVEN data on atmospheric composition and the measurements of heat flow suggest ongoing internal processes that could power volcanism. It might not be continuous. It might come in pulses, with long periods of quiescence interrupted by brief episodes of activity. But the possibility that Mars could erupt volcanically in the near future in human terms, within the next few million years, or even sooner, cannot be ruled out based on current evidence. This discovery completely overturned the old narrative of Mars as a geologically dead world that cooled 3 or 4 billion years ago. Instead, the picture that emerged of a world that cooled more slowly than expected, that retained pockets of heat in its interior, that experienced episodes of volcanism later in its history than simple models predicted. A world that, while not as geologically active as Earth, was far more active than previously assumed. Another discovery that shattered the old Mars consensus was evidence that Mars's crust is still deforming tectonically. While Mars plate tectonics, as we know them on Earth, there's no evidence for large lithospheric plates grinding past each other. The crust isn't simply static and inert. It's moving, it's cracking, it's spreading. The deformation is slow. It's real. The Valles Marineris Canyon system provides the most dramatic evidence. This vast network of canyons stretches over 4,000 kilometers across Mars's equator, cutting deeper than anywhere else on the planet. with some sections plunging 7 kilometers below the surrounding terrain. For decades, scientists debated how valles marineris formed. The leading hypothesis involved tectonic extension, the crust being pulled apart, with massive blocks subsiding to create the deep valleys. This made sense because Mars shows regional patterns of extension in several areas. But what was causing this extension? Why was the crust being pulled apart? The answer lies in the structure of Mars's lithosphere. Under the Tharsis region, the crust and upper mantle are thicker than elsewhere. This creates a massive weight that depresses the underlying mantle. The depressed region creates pressure, which pushed laterally, putting the surrounding regions under stress. This stress, called Tharsis rise stress, pulls the Martian crust apart in certain directions. The extension creates fractures and grabens blocks of crust that subside as the crust stretches. Valles marineris is the most dramatic expression of this stress. But here's what matters for the active Mars story. This tonic stress is still present. The crust is still being pulled apart. The fractures created by this extension are still present, and some appear to show signs of recent rupturing. The Cerberus fossae, a series of straight-line fractures in the Elysium region, show evidence of repeated opening and extension. Some of the fractures have young lava flows in them, suggesting magma has recently exploited these weaknesses to reach the surface. The fractures themselves show no significant erosion, suggesting they're relatively young. Some researchers have proposed ages as recent as a few million years or even younger. This is tectonic activity, the same kind of process that creates earthquakes on Earth, that forms rift valleys, that drives the motion of continents. The style is different because Mars isn't operating plate tectonics. But the process is the same: stress in the crust, deformation, faulting, and the possibility of earthquakes. And indeed, the marsquakes detected by InSight's seismometer are evidence of exactly this kind of owing tectonic stress. The quakes cluster around tectonically active regions like Cerberus fossae, confirming that these regions are still under stress, still deforming, still shaking. The global stress patterns on Mars reveal something else interesting. The stress isn't randomly distributed. It follows patterns. The Tharsis rise stress creates a global pattern, with extension in certain directions and compression in others. This pattern has been deforming Mars's crust for billions of years. It's responsible for the distribution of volcanic features, canyons, and structural patterns we observe across the planet, and it's still operating. The stress is still there. The deformation is ongoing. Some of the most interesting recent tectonic features involve young places where the crust is pulling apart and new fractures are forming. These rifts are associated with centers of active volcanism, or with regions where mantle plumes are bringing hot material toward the surface. The rifts allow magma to reach the surface more easily, which is why the youngest volcanoes on Mars are concentrated in regions with clear rift structures. The Elysium region again provides the prime example. Active rifting, young volcanism, recent lava flows, and ongoing seismic activity all concentrated in the same area. What's particularly significant that all of this tectonic activity is powered by Mars's internal heat and by the stress structures created by planetary mass distribution. It's not externally driven. It's not dependent on Mars's surface or in the atmosphere. It's a result of Mars's interior doing what interior mantles do on any planetary body. They convect, they generate heat, they create stress, they drive deformation. Mars' interior is still doing this, still generating the stress that's deforming the crust, still allowing magma to rise and volcanoes still causing earthquakes. While the large-scale process volcanism, tectonics, water cycling get most of the attention, there's another category of active processes happening on Mars that occurs at the chemical level. Mars's surface is still reacting, still weathering, still changing composition through interactions between rocks, water, ice, and atmosphere. The rovers that have explored Mars's surface have performed detailed chemical analysis of rocks and soil. Curiosity, which landed in Gale Crater in 2012 and is still operating, carries a drill that can bore into rocks, extract samples for analysis. These samples are heated and analyzed by the SAM instrument, which breaks down the rocks into their chemical constituents. The data from these analyses reveals a surface that is far more complex chemically than anyone predicted. Mars's surface contains minerals that require specific conditions to form. Jarosite is a mineral that forms when sulfuric acid-rich water chemically weathers rocks in acidic, aqueous environment. The presence of jarosite on Mars indicates that Mars had periods when liquid water was present and acidic, interacting with surface rocks. These periods were primarily early in Mars's history, in the first billion years. But the jarosite hasn't been completely destroyed. It persists on the surface, evidence past aqueous chemistry. More intriguingly, Curiosity detected perchlorate in Mars's soil and rocks, perchlorates that form through oxidation reactions. Their presence suggests that Mars's soil has been processed by oxidizing conditions where electron-stealing reactions occur at the surface. The oxidizing agent appears to be hydrogen peroxide, which forms when solar UVB radiation breaks apart water molecules. The hydrogen peroxide reacts with iron minerals in the soil to create perchlorates. This process is still happening today. Every time solar UVB radiation breaks apart water molecules in Mars's thin atmosphere, and these molecules interact with soil, more perchlorates can form. It's a slow chemical process, but it's actively occurring. Curiosity also found evidence of seasonal variations in atmospheric chemistry. As seasons change and atmospheric circulation patterns shift, the composition of the air changes. These changes appear to affect surface chemistry. Rocks that were exposed to one atmospheric composition in one season are exposed to a different composition in another season. Over time, these varying conditions create a weathering pattern. The rocks are being altered slowly by the changing atmosphere and changing conditions. This is chemical weathering in action, happening on Mars right now. The discovery of organic compounds in Mars's rocks and soil was another surprise. These compounds were not initially understood. Early speculations ranged from the remains of ancient microbial life to contamination from Earth. The rovers were sterilized, but couldn't be completely contaminated. But detailed analysis showed that the organics present are consistent with non-biological chemical reactions. Organic molecules can form when minerals are exposed to solar UV radiation, process called photochemistry. Specifically, when rocks containing iron minerals are exposed to UV and to water humidity, chemical reactions can create simple organic compounds. This process would be happening on Mars now, creating a very slow accumulation of organics on the surface through purely chemical means. More recent studies how Mars's soil composition changes with depth. When the rovers drill into rocks, the fresh material exposed can be compared to surface material that's been weathered. The differences reveal how weathering operates on Mars. The rates are slow. Mars's weak atmosphere and lack of liquid water on the surface mean weathering is orders of magnitude slower than on Earth. But it's measurable, it's quantifiable. Over millions of years, significant changes accumulate. The soil at Mars's surface is also rich in certain elements like sulfur and chlorine, which suggests that these elements have been leached from rocks through aqueous weathering and then concentrated in the surface soil as water evaporated or moved deeper. This process requires water-rock interaction, which must have been most active early in Mars's history when liquid water was more abundant. But the residual effects persist. The enriched soils remain evidence of the interaction, and in certain regions, particularly near subsurface ice, seasonal moisture exchanges, some water-rock interaction, might still be occurring at a very slow rate. Curiosity has also detected variants in methane concentration at the landing site that correlate with temperature and atmospheric pressure changes. This suggests that methane is bound in the soil itself, perhaps trapped in mineral structures or in subsurface ice, and is released or reabsorbed seasonally as conditions change. The methane that was detected early in the Rovers mission, but diminished later, might reflect seasonal variations in how much methane is released from the subsurface into the atmosphere. This means Mars's subsurface isn't just cold and inert. It's responding to surface conditions. It's exchanging volatiles with the atmosphere. It's an active system, albeit operating at a glacial pace compared to Earth. The presence of sulfates in certain regions indicates that acidic water interacted with rocks. The presence of clays indicates neutral to slightly alkaline water. Different regions show different mineralogical signatures, which suggests that the water chemistry varied across Mars or changed over time. These mineralogical patterns form a record of Mars's aqueous history, but they also suggest ongoing weathering, because newly exposed surfaces show different properties than old, weathered surfaces. The differences are subtle, but they indicate that surface processes are still occurring. Dust sounds mundane. It sounds like something boring fine particles that get in equipment, that blur images, that on solar panels. But Martian dust tells a story of planetary activity. The dust exists because something is creating it, and what's creating it is weathering, erosion, and the transport of material across the planet by wind. The particle-size distribution of Martian dust is interesting. Dust on Mars ranges from very fine particles, only a few micrometers across, to larger grains. The finest dust persists in the atmosphere longest, is transported farthest, and eventually settles out everywhere on Mars. This means that dust observed in one region might have originated hundreds or thousands of kilometers away. Dust storms, particularly the seasonal global dust storms that rise in Mars's southern hemisphere during spring and early summer, mobilize and transport massive quantities of dust across the planet. The 2018 global dust storm that contributed to Opportunity's demise demonstrated this dramatically. The storm rose over Mars's southern highlands, grew into a planet-encompassing veil, and cut off sunlight to the rest of Mars for months. The dust storm is an atmospheric circulation process driven by solar heating of the surface and seasonal pressure variations. It's not a permanent feature. It fades. But its recurrence demonstrates that Mars's atmosphere is still capable of dramatic activity, still capable of moving material across the planet, still capable of reshaping the surface through erosion and deposition. Dust devils rotating columns of air similar to terrestrial tornadoes, but typically weaker, have been photographed by the rovers and observed from orbit. These whirlwinds form when solar heating creates thermal instability in the lower atmosphere, allowing air to rise in spiraling columns. The dust devils visible from orbit appear as dark tracks where dust has been swept aside, revealing the darker rock beneath. The recurrence of dust devils season after season shows that this atmospheric process is ongoing and regular. Dust devils are moving dust, eroding surfaces where they pass, and actively reshaping the landscape in visible ways. Chemical composition studies of the dust reveal that it's not uniform across Mars. Dust from different regions has different mineralogical compositions, reflecting the underlying geology. Atmospheric studies that analyze dust composition can therefore track where dust comes from and where it's being transported. This reveals dust transport patterns, seasonal wind patterns, preferred transport directions, and the long-range movement of material. All of this indicates active atmospheric circulation and material transport. More remarkably, orbital observations have revealed that certain regions accumulate dust preferentially. Dust deposition patterns aren't uniform but follow patterns determined by atmospheric circulation and prevailing winds. When the same region is observed in successive years, dust coverage changes, revealing that dust is constantly being added or removed. This is weathering in action. The fine dust that falls gradually covers them, is then blown away by wind, is picked up and transported elsewhere. It's a cycle of dust creation and transport that's actively occurring on Mars. The dust in Martian soil has been chemically altered by radiation and oxidation. The oxidation state of iron minerals in the dust is higher than the oxidation state of iron in fresh rock. This indicates that the dust has been processed by oxidizing conditions, which results from interactions with hydrogen peroxide and other oxidants produced by UV photochemistry. The more oxidized dust has been at the surface longer, has undergone more chemical weathering. The process is ongoing. Fresh dust created from the breakdown of larger rocks is less oxidized. Over time, it will be oxidized. Then it will be transported. Wind will settle out, accumulate in certain regions. This dust cycle is active now. Mars's polar regions are not static, frozen wastelands. They're dynamic, changing, and active in multiple ways. Both the North and South polar ice caps contain water ice, though the exact amounts and distributions were not definitively known until recent orbital measurements. The North Polar Cap is primarily water ice, with a thin seasonal layer of carbon dioxide frost on top during winter. The South Polar Cap is a mixture of water ice and carbon dioxide ice. The carbon dioxide ice is the more volatile component. It sublimates, turns directly from ice to gas, when temperatures rise slightly. This causes the South Polar Cap to shrink and grow more dramatically than the North Cap with seasonal changes. As Mars orbits the Sun, the seasonal pressure changes cause carbon dioxide evaporate from the South Polar Cap during Southern Hemisphere summer and redeposit during winter. This creates atmospheric pressure variations visible in measurements from the rovers and orbiters. The pressure can vary by up to 30% between summer and winter. This extreme seasonal variation that Mars's atmosphere is actively exchanging volatiles with the surface, particularly with the polar ice caps. It's not a static reservoir. It's dynamic and changing. The polar layered deposits layers of ice and dust that form the bulk of the polar caps preserve a record of Mars' climate history. Scientists studying these layers using radar and imaging instruments have found patterns suggesting different climate regimes at different times in Mars's history. Some layers are thick, suggesting periods of heavy ice and dust deposition. Others are thin, suggesting relatively dry periods. The layering indicates that Mars has experienced climate cycles, with variations in atmospheric pressure, temperature, and water availability repeating over time. More intriguingly, some of the youngest polar deposits appear to still be actively accumulating. Fresh snow can be detected in certain regions during particular seasons. Frost patterns near the poles show signs of being actively created and destroyed. The polar regions, just museums of Mars's past. They're regions where water is still being exchanged with the atmosphere, still moving around, still responding to seasonal changes. The exchange rates are slow, but they're measurable. The spiral troughs that form the distinctive terrain of the polar caps also appear to be actively eroding. These troughs are formed by sublimation of ice and the removal of material by wind. Analysis of orbital imagery over decades suggests that the troughs are getting deeper and more pronounced in some areas. Material is being removed. The landscape is changing. It's slow. The changes happen over decades or centuries, but they're real, measurable changes to the polar landscape. Radar-based observations have revealed subsurface pockets of liquid water beneath the polar ice caps. These are salty water reservoirs where perchlorates or other dissolved salts lower the freezing point enough to keep water in liquid form even at temperatures of -50 to -7 degrees Celsius. If these reservoirs exist, they represent potential habitats for microbial life. But for the present discussion, they represent active subsurface water that's not completely frozen, water that's participating in chemistry and potentially moving around through subsurface pores and fractures. All of these active processes, the seismic activity, the methane emissions, the seasonal water cycling, the subsurface heat, the ongoing chemistry converge on a single question: could Mars harbor life today? The surface of Mars is hostile. Temperatures are far below zero. The atmosphere is so thin it offers little protection from radiation. Dust contains perchlorates that would be toxic to Earth biology. Liquid water doesn't exist at the surface. There's no obvious energy source that would support a local biological ecosystem. But the subsurface is different. Below the radiation-blasted surface, temperatures increase with depth. The geothermal gradient, the rate at which temperature increases with depth, suggests that at depths of a few hundred meters, temperatures could be warm enough for liquid water to exist if salts are present to lower the freezing point. The subsurface contains water ice and potentially liquid brines. The subsurface contains heat from radioactive decay and possibly from ongoing volcanic or hydrothermal activity. The subsurface contains chemical energy, the potential for energy-releasing reactions between different chemical species. These conditions are similar to subsurface environments on Earth, where chemolithotrophic life exists, life that derives energy from chemical reactions between rocks and water, without requiring sunlight. In certain regions of Earth's subsurface, microbes live kilometers below the surface, deriving energy from the slow oxidation of minerals. If similar environments exist on Mars, similar life could potentially survive there. The methane question is central to this discussion. If Mars is producing methane now, and if biological processes could generate methane, then the presence of methane could indicate life. But we know methane can also be produced through biological chemistry. The methane detections don't prove life exists, but they suggest that biological precursors, the chemical building blocks life needs, the presence of liquid water, the presence of energy sources, could exist on Mars. More tangibly, Various missions have shown that Mars has the chemicals necessary for life. Carbon is present, nitrogen is present, phosphorus, sulfur, and other essential elements have been detected. Water ice is as abundant. There are energy sources, heat from the interior, chemical gradients between different mineral types in the presence of water. There are potential environments, subsurface pores, cracks in rocks, cavities in lava tubes, where life could exist protected from surface radiation. What's missing is direct evidence. No rover has detected life. No mission has found fossils or organic structures that could only come from living organisms. The odd compounds detected by curiosity can be explained through chemistry. The methane could be geological. The gullies could result from dry processes that don't require liquid water. But the point is that Mars is no longer obviously uninhabitable. The old model, a dead, inert world with nothing happening, with no liquid water, with no chemical activity, with no energy available, has been thoroughly disproven. Mars has subsurface water. Mars has heat. Mars has chemical potential. Whether life emerged on Mars in the past and persists in subsurface refuges today remains an open question. But the fact that it's an open question represents a complete reversal from the old consensus that Mars was obviously sterile. The Perseverance rover, which landed in Jezero crater in February 2021, represents the latest iteration of Mars exploration. Perseverance is larger than Curiosity, more capable, and specifically designed to search for signs of ancient microbial life. One of its primary missions is to collect rock samples that will eventually be returned to Earth by a future sample return mission. The hope is that Earth-based laboratories, with their sophisticated equipment, will be able to definitively determine whether Mars's rocks contain evidence of past life. But Perseverance is also providing new real-time data on current conditions. The rover has detected organic compounds. It has measured atmospheric variations. It has recorded sounds, the first audio recordings from Mars, which reveal wind, rover vibrations, and equipment operation. Perseverance is demonstrating that Mars is a complex place with ongoing processes that create dynamic conditions. Jezero crater itself is particularly interesting. The crater contains a river delta, clear evidence that water once flowed there. That water pooled in a lake that filled the crater. The delta deposits contain clay minerals that form in neutral pH water, suggesting that the environment might have been habitable for Earth-like life at some point in the distant past. Perseverance is exploring this ancient habitable environment, looking for fossil signatures, looking for evidence that life did indeed emerge, persist during the time when Mars was warmer. Equally important, future missions are planned that will continue this scientific revolution. The Rosalind Franklin rover, currently part of the ExoMars mission, is equipped with a drill that can bore much deeper than previous rovers, up to 2 meters down. At that depth, the subsurface should be better from radiation, and the temperature should be slightly warmer. If subsurface life or biosignatures exist on Mars, the D samples are more likely to reveal them. The Zhurong rover from China has explored regions that previous missions haven't covered, providing data from different parts of Mars. Multiple orbital assets continue to gather data, with instruments becoming more sophisticated. The MAVEN mission continues to study atmospheric loss and exospheric chemistry. The InSight mission provided seismic and heat flow data that revolutionized our understanding of Mars's interior. Looking further ahead, NASA and other space agencies are planning a sustained presence on Mars. Humans will eventually land and establish bases. Those bases will require water, and the subsurface water sources that geophysical surveys are now identifying will be critical. The human missions will also enable geological investigation at a level far beyond what rovers can achieve. Humans can explore more quickly, cover larger areas, use intuition and adaptive science that rovers cannot. The scientific questions about Mars's present activity and past history will drive many of these human investigations. The story of Mars's resurrection from dead world to active, dynamic planet has profound implications that extend far beyond Mars itself. It changes how we think about planets, how they evolve, and what conditions they need to remain geologically active. First, it demonstrates that size alone doesn't determine a planet's fate. Mars is small, but it's not completely dead. Earth, being larger, will remain geologically active longer than Mars. But Mars shows that even a small planet can sustain internal heat and activity for billions of years. The estimates for how long Mars's interior will remain active have been extended. Some current models cite Mars's localized volcanism and chemical activity for tens of billions of years, much longer than earlier models predicted. Second, it shows that planetary habitability is more nuanced than simple models suggested. We used to think that a planet either has liquid water on its surface and is potentially habitable, or it doesn't and it's sterile. Mars challenges that dichotomy. Mars lacks surface liquid water, but it likely has subsurface reservoirs. Mars lacks a thick atmosphere and magnetic shield, but it has subsurface environments protected from radiation. The conditions for life, or the remnants past life, aren't necessarily obvious from orbit. They require detailed investigation. Third, it expands our thinking about where and how to search for life beyond Earth. If life can persist in subsurface environments on Mars, it suggests that similar environments might exist on the moons of Jupiter and Saturn, Europa, Enceladus, and others, where subsurface oceans exist beneath ice shells. The fact that Mars is showing signs of ongoing habitability increases the probability that these other worlds are also habitable, or have been in the past. Fourth, it refines our understanding of planetary evolution. We now know that planets don't simply cool smoothly. They can experience episodic activity. They can have regions where heat remains concentrated longer. They can sustain localized processes even as the overall planetary trend is toward cooling. This has implications for how we model planets around other stars. If we know a planet is a certain age and a certain size, we can now make better predictions about whether it's still geologically active, whether it might have surface conditions suitable for life, whether it might be worth investigating as a potential habitat. Finally, it illustrates the importance of sustained investigation. Mars wasn't fully understood until we sent multiple missions to better instruments and looked at the planet over extended time periods. The Mars story required decades of observation. Mariner, Pathfinder Global Surveyor, Odyssey Mars Express, Reconnaissance Orbiter, Phoenix, Spirit, Maven, Insight, and Perseverance. Each mission added pieces to the puzzle. Together, they created a picture that contradicts the old model. This lesson is relevant for future exploration of other planets and moons. Deep understanding requires sustained effort. The methane question deserves more detailed exploration because it remains one of Mars's most perplexing mysteries and potentially of the most significant for astrobiology. The first detection of methane created excitement because it suggested active processes on Mars. But over subsequent years, the story became more complicated. Ground-based telescopes from Earth sometimes detected methane, sometimes didn't. When they did detect it, concentrations varied. Orbital measurements from Mars Express agreed that methane was present, but couldn't pin down exactly where it came from or how much there was. The most intense scrutiny came when Curiosity and Gale Crater. The rover had its own methane equipment as part of the SAM instrument suite. Curiosity could measure atmospheric methane at ground level in real time. As the rover drove across the crater floor, the data was fascinating and contradictory. Sometimes methane levels would spike dramatically, sometimes they would be low. The variations seemed to happen without any obvious pattern tied to season or time of day. One particularly intriguing series of observations involved methane vents at Gale Crater that showed tenfold variations. Sometimes methane was present at one concentration, sometimes 10 times higher. These weren't gradual changes. They were dramatic spikes. Something was releasing methane pulses into the atmosphere. But what? Several hypotheses emerged. One involved subsurface methane being released through fractures or soil pores in response to pressure changes. As atmospheric pressure changed with the seasons, the pressure difference between the atmosphere and the subsurface would vary. During low-pressure periods, subsurface, including methane trapped in the soil or in subsurface ice, might be forced upward and escape to the atmosphere. This would create periodic pulses tied to atmospheric pressure cycles. Some of the methane spikes seem to correlate with low-pressure days, lending support to this hypothesis. Another hypothesis in biological methane production in subsurface biofilms. If microbes exist in pockets of subsurface water on Mars, they could produce methane as a metabolic byproduct, just as Earth's methanogens do. The methane would accumulate, then be released as pressure changes or as seasonal warming allows diffusion upward. This would also create periodic releases, though the periodicity might be less regular than purely physical processes would produce. A third hypothesis involved clathrite moleculages of ice that can trap methane. If Mars's subsurface contains methane clathrates, warming could destabilize them, releasing the trapped methane. This process would be temperature-dependent, happening more in summer or in warmer regions. But the Gale Crater measurements didn't show obvious summer peaks as this hypothesis would predict. More recently, some researchers have proposed that the methane variability isn't real, that it's an artifact of how the SAM instrument is operated or calibrated. Extraordinary claims require extraordinary evidence, and the claim that Mars is actively losing methane is extraordinary. Some skepticism is warranted, but the fact that multiple instruments on multiple missions have detected methane suggests that the signal is genuine, not an instrument artifact. What's particularly interesting is that some of the methane spikes seem to come from the local area around Curiosity's current location, rather than being global atmospheric changes. This suggests point source-specific locations where methane is being released. If true, this has enormous implications. It would mean Mars has regions of outgassing, regions where subsurface volatiles are reaching the surface now. The regions would become prime targets for future exploration and sample collection. The methane mystery remains unsolved. Current data and current understanding insufficient to definitively explain what's producing the methane, how much is being produced, or what mechanism is responsible. The Perseverance rover includes improved methane detection instruments. Future missions will carry even more sophisticated instruments, Eventually, the methane question will be resolved. But for now, it remains one of the most tantalizing pieces of evidence that Mars is still active, still doing something beneath its thin atmosphere and frozen surface. Beyond the question of whether liquid water exists in Mars's subsurface, there's a deeper question of what that water is doing. What is its chemical composition? What reactions could occur in Mars's subsurface aqueous environments? What could water-rock interactions produce? The minerals detected on Mars's surface provide clues about the subsurface water chemistry. Salts that are more soluble in water and less stable at the surface must have formed in subsurface conditions and then been brought to the surface by geological processes or by upwelling of subsurface fluids. The presence of perchlorates and other oxidizing salts suggests that Mars's subsurface water, at least at some times and places, was quite oxying, a condition that would support certain types of chemical reactions. The presence of sulfate and chloride minerals suggests acidic to neutral pH conditions, with sulfur and chlorine being released from mineral dissolution or from volcanic outgassing. These salts would lower the freezing point of water, allowing liquid water to exist at subsurface temperatures that would otherwise keep water frozen. So Mars's subsurface water isn't pure H2O. It's brine salty water, and the chemistry of this brine would govern what reactions are possible. One particularly important reaction is the serpentinization process as mentioned earlier. When olivine and pyroxene minerals, iron, magnesium, silicates common in Mars's cratertic crust react with water, particularly in the absence of oxygen, they produce hydrogen gas and methane. The reaction is energetically favorable and releases heat. On Earth, serpentinization occurs at mid-ocean ridges and in other subsurface hydrothermal systems. It's a major source of hydrogen and methane in Earth's subsurface. If Mars has subsurface water interacting with its abundant iron and magnesium silicate minerals, serpentinization could be occurring on Mars as well. The hydrogen produced by serpentinization can itself undergo further reactions. In the presence of other oxidants, and with microorganisms as catalysts, hydrogen can be oxidized to produce water and energy. This energy could theoretically support simple bacterial metabolism. So serpentinization wouldn't just produce methane, it could create the chemical gradients and energy gradients necessary for metabolism. This is why serpentinization is often looked as a potential energy source for subsurface life on Mars. The thermal conditions deep in Mars's subsurface could also support more complex water rock reactions. If the subsurface is heated enough by geothermal gradients, or by proximity to magma chambers or hydrothermal vents, the water temperature could reach several tens of degrees Celsius. At these temperatures, many chemical reactions would proceed faster. Minerals would dissolve more readily. Organic compounds, chemical bonds would break and reform more quickly. The problem is that we can't directly sample Mars's subsurface to measure the actual composition of subsurface water, or to confirm that these reactions are actually occurring. We have to infer conditions from surface mineralogy, from theoretical models. The inferences suggest that subsurface conditions could be conducive to chemistry and potentially to life. But direct proof awaits future sample collection and analysis. If Mars had subsurface liquid water, if it had heat, if it had the chemical ingredients for life, then life might have emerged on Mars in the past. The conditions would have been right. The chemistry would have allowed it. The energy sources would have been available. The biggest remaining question is whether life actually did emerge on Mars. And if it did, whether traces of it persist today, or whether it went extinct and is now only visible in fossilized form. Early Mars was warm and wet, this much is clear from geological evidence. The period from roughly 4 billion to 3.8 billion years ago saw widespread liquid water on Mars's surface. Rivers flowed. Lakes formed. Deltas accumulated sediments. This period is called the Noachian era, and it's sometimes called early Mars. During this time, Mars would have been far more habitable than it is today. If life was going to emerge on Mars, this would have been the time. The evidence suggests that Mars became drier over time. The magnetic field shut down around 4 billion years ago. This allowed the solar wind to begin stripping away the atmosphere. The atmospheric loss accelerated. Water disappeared from the surface. By around 3 billion years ago, Mars had entered a different climate regime, one characterized by cold and dryness. Some liquid water would still have existed subsurface, but surface conditions became increasingly harsh. If life emerged during the warm, wet early Mars period, it would have had to adapt to the gradually changing conditions. Some organisms might have migrated deeper underground to subsurface environments where conditions remained relatively stable. Life might have persisted in subsurface aquifers, using chemical energy from mineral-water interactions, surviving in darkness and cold but protected from radiation. Over the past 3 billion years, Mars has cooled and dried further. If life persists today, it would be deep underground, in small pockets of liquid water, exploiting the remaining chemical and thermal energy. The population would likely be sparse. The metabolism would be slow. Detection would be difficult, but traces might persist. Fossils in ancient rocks brought to the surface by impacts, biosignatures in chemical anomalies, or even living organisms that could be awakened if brought into suitable conditions. The rovers have searched for these signs. Curiosity has analyzed thousands of rock samples, looking for organic compounds, isotopic anomalies, or other signatures of past life. Perseverance is continuing this search. To date, no unambiguous evidence of life has been found. But the absence of obvious signatures doesn't rule out life's existence. Ancient biosignatures can be destroyed by radiation, by oxidation, by chemical alteration. Life might have existed on Mars, but left no easily detectable trace. The best hope for detecting past Martian life might come from drilling deep into the subsurface to analyses that have been protected from the harsh surface conditions. Near high thermal activity near young volcanoes or hot springs might preserve better evidence, or regions where organisms might persist today, still in subsurface water, could provide unambiguous evidence of past or present Martian life. The search continues. Future rovers, human explorers, and advanced analytical techniques will keep looking. Mars's active interior, its subsurface water, its ongoing chemical processes, all of these create the possibility life did or does exist on Mars. That possibility is no longer dismissed as fanciful. It's considered a scientific hypothesis worth testing. Understanding Mars's activity and evolution provides context for understanding planetary evolution generally. Comparing Mars to other worlds reveals patterns and processes that might apply across many planetary systems. Venus, larger than Earth and closer to the Sun, had an entirely different evolutionary path. Venus became a hellscape world with surface temperatures hot enough to melt lead, an atmosphere so thick the pressure would crush structures, clouds of sulfuric acid. Venus's internal activity is strong. It has active volcanism and tectonic processes today. but the surface conditions are so extreme that they're incompatible with life as we know it. Venus represents what happens when a planet is too close to its star, even if it's large enough to maintain internal activity. Mercury, smaller than Mars, cooled faster and developed a thinner exosphere. It lacks subsurface water, yet, as explored in the first part of this narration, Mercury is showing surprising activity, releasing volatiles into its exosphere. Mercury demonstrates that even a small planet, ongoing processes, even if those processes are fundamentally different from what we see on Mars. Earth remains a giant compared to Mars, larger, warmer, with a protective magnetic field and a thick atmosphere. Earth's geological activity is orders of magnitude greater than Mars's. But the basic processes are the same. Earth's volcanoes erupt. Earth's crust deforms. Earth's surface responds to internal and external forcing. Earth demonstrates what a geologically active world looks like. The moons of the giant planets Europa, Enceladus, Io, and others show that size isn't everything. Europa is small and distant from the Sun, but tidal heating from Jupiter keeps its subsurface warm and maintains an ocean beneath its ice shell. Enceladus, similarly heated by tidal friction from Saturn, has active geysers and ongoing outgassing. These worlds demonstrate that activity can come from multiple sources, not just internal radioactive decay, but also tidal heating, gravitational interactions with larger bodies, and other mechanisms. Mars sits in the middle of this spectrum. It's larger than the moons but smaller than Earth. It's far enough from the Sun to be cold, but close enough to receive significant solar energy. It has subsurface water and internal heat, but not enough to create surface oceans or global magmatism. Represents a particular state, not fully dead, not fully active, but somewhere in between. Understanding Mars helps us understand the range of planetary possibilities. For exoplanets, Mars is crucial context. Many exoplanet discoveries involve small rocky planets orbiting in or near the habitable zone of their star. We wonder whether these worlds are likely to be geologically dead and sterile, or whether they might maintain activity and habitability despite their small size. Mars suggests that small planets can be active. Mars suggests that even a dead world isn't necessarily sterile or simple. Mars suggests that the range of planetary environments is broader and more diverse than simple models predict. We stand at a critical juncture in Mars exploration. The rovers and orbiters have given us an unprecedented understanding of Mars. They've shattered old assumptions and opened new questions. The next phase of exploration promises to go deeper and to stay longer. Planned human missions to Mars represent a watershed. The first humans to set foot on Mars will conduct science impossible for rovers to perform. They'll drill deeper, explore faster, make intuitive connections that algorithms can't. They'll establish scientific bases that can operate continuously, studying seasonal changes, monitoring seismic events, and investigating subsurface resources. The human bases will need water, and now we know where to look for it. The geophysical surveys have identified regions with accessible subsurface ice. Future human explorers will extract this water for drinking, for creating fuel for the return trip, and for scientific investigation. The water will likely contain salts and dissolved minerals. Its exact composition will be measured. The chemistry will be analyzed. If this subsurface water is active, if it's exchanging with the atmosphere, or participating in rock-water reactions, its composition will reveal clues about Mars's subsurface environment. Future rovers will carry even more sophisticated instruments. Drills will bore deeper, accessing samples depths where protection from radiation is greater. Spectrometers will achieve finer chemical resolution. Sensors will measure heat flow, seismic activity, and magnetic fields with unprecedented precision. Sample missions bring Martian rocks back to Earth, where they can be analyzed in laboratory conditions that rovers can't replicate. The search for biosignatures evidence of present or life will intensify. Rovers will look in places most likely to preserve or harbor life, near hydrothermal sites, in clay-rich deposits, in caves that radiation protection, in subsurface environments accessed through drilling. The analogs on Earth will guide the search. Scientists will study Earth's subsurface life to understand what signs to look for on Mars. Simultaneously, the question of habitability will be refined. We'll better understand Mars's current water budget, how much water exists, where it is, whether it's accessible. We'll better understand the heat budget, how much heat is available in different regions, whether that heat could power subsurface chemistry or even biology. We'll better understand the chemical budget, what reactions are possible in Mars' current environment, what energy those reactions could provide. Over the next few decades, the cumulative weight of evidence will likely resolve several of the major mysteries. Either we'll find definitive evidence that life existed on ancient Mars and persists today, or we'll establish that Mars, despite its activity, never developed life or lost it long ago. Either we'll discover that subsurface habitable zones are extensive and accessible, or that they're rare and isolated. Either we'll determine that Mars's activity is sufficient to support ongoing processes, or that it's tapering toward complete dormancy. Whatever we find, the story will likely be complex. Mars won't be simply alive or simply dead, simply habitable or simply sterile. It will be a world of zones, some regions more active than others, some potentially habitable, others barren. A world of history, with traces of its warmer, wetter past visible in its geology, evidence of its gradually changing conditions preserved in layers of rock. A world of ongoing processes, seismic rumbles, thermal variations, chemical reactions, water cycles, all still awaiting, but at a slower pace than on Earth. We began with the assumption that Mars was dead. That assumption was wrong. Mars is not what we thought. Not because Mars changed, but because our understanding changed. We looked deeper. We sent better instruments. We gathered more data. We let the data challenge our assumptions. What emerged is a portrait of a planet that is far more dynamic and complex than the simple narrative of planetary death suggested. Mars has an active interior that generates heat and seismic activity. Mars has water in multiple forms and in multiple locations. Mars has chemical processes ongoing at its surface and subsurface. Mars has an atmosphere that moves and changes, that interacts with the surface and exchanges volatiles on seasonal timescales. Mars is not Earth. It's not a geologically hyperactive world with plate tectonics and continuous volcanic eruptions and oceans and weather. But it's not a frozen, dead rock either. It's something in between. It's a world where processes continue, albeit slowly. A world where energy, thermal and chemical, is still available. A world where conditions might permit life to persist in deep refuges, even if the surface is hostile. A world where the possibility of discovery remains open. The story of Mars is a story of scientific revolution. It shows what happens when new data challenges old models. It's the importance of sustained investigation and multiple perspectives. It shows that our understanding of worlds can be completely overturned by new evidence. It shows humility in the face of nature. Nature is more complex, more nuanced, more surprising than our models anticipated. For the future explorers of Mars, this is exciting. The mysteries remain. The questions about past life, present activity, surface habitability all remain open. Each new mission brings more data. Each new analysis reveals more complexity. Mars has not finished surprising us. It refuses to stay still, refuses to be simple, refuses to be the dead world we thought it was. In the decades ahead, humans will walk on Mars. They'll conduct science in ways rovers cannot. They'll drill into the subsurface. They'll collect samples from regions rovers haven't reached. They'll ask questions and investigate answers in real time, adapting to what they find. What they discover might transform our understanding of habitability, of life's potential in the universe, of our own place in the cosmos. Mars is not literally, but in our understanding of it. What it reveals in the coming years could rewrite the story of planets and life. The greatest discoveries might still be ahead.